Chapter 6. So methods for two independent samples. We will finish section 6.1 in this video. That's a lot. Then that's from slide 1 to slide 42. Then we will finish the rest of the chapter in next video. So, which is not that much. Okay. So we have learned the statistical testing methods for single samples and paired samples. We have discussed that some methods can be extended to deal with two samples. Right. Now let's learn those two sample problems and methods. For two samples, the things we test are similar to single sample or paired sample. For two samples, we may compare and estimate their centrality and compare two samples' median, or talk about their normal scores, compare their variance, test if they have a common distribution. Then we will summarize the field of application. So because this course is designed as a practical course, we focus more on how to use the methods rather than the mathematical theories and principles behind each method. So we will only introduce the ideas and concepts of the methods roughly, but we do not require you to memorize or manually calculate the thing. But you need to know how to operate the corresponding functions in R. So those functions and codes in R will be given for you to do homework and exam. So let's first start with section 6.1. First, let's talk about the centrality tests and estimates of two samples, which are extension from single samples. There are multiple ways to extend the methods for the single samples to deal with two samples or multiple samples. The common methods we use for testing two samples include the ones we have learned: Wilcoxon-Mann test, Kolmogorov. So the methods we will introduce in this chapter are all extensions based on what we have learned. No new methods. So for two independent samples, the analog of the one sample Wilcoxon rank test is the Wilcoxon rank sum test. An equivalent test used more common in medical world is this one, Wilcoxon-Mann-Whitney test. Sometimes we call it WMW for short, or we write it WMW for short. So how does it work? It works like this. Given two samples, we combine them as one big sample and get the joint ranking of each observation in this big sample. Then we calculate the sum of the joint ranks of all observations in each sample as S1 or S2. And sometimes we write it as SM and SM. M and N are the sample size for sample 1 and sample 2. So by comparing these two values here, S1 and S2, or SM and SM, we make a conclusion whether the two processes or two populations have the same or similar center. We use median to assess this center. Let's look at examples. So example 6.1. Okay, let's go to the textbook to skim the problem. It's better than just read by me. So it's on page 152, example 6.1. There are two models of calculators in terms of running the trigonometric functions like sine, cosine, tangent, those functions. in triangle problems. So type 1 model is pressing the number first, the degree first, then pressing the function button, like 30 degree, then press sign. Type B is the opposite, pressing the function first and then pressing the numbers. So a math teacher wants to find out if one model makes students solve trigonometric problems faster than the other model does. To carry out this experiment, a class of 21 pupils are randomly divided into two groups, Group A and Group B. Group A with 10 students using type A calculator, and Group B with 11 students using type B calculator. They do the same set of trigonometric problems. Here are the times of each student in Group A and Group B completing the problems. The unit is minute. They're in minutes. So do the data indicate that one model is faster than the other? So this is the problem statement. Then let's go through our regular procedures, which is the formulation and talk about assumptions, then look at the results, make a conclusion, then give comments, then look at the computational aspects. So first, formulation. This is to test if the two samples have the same median. And so this is a two-tailed test, right? We don't know which one may be faster, which group, which model may be faster than the other. We just want to test if they are different. So the null hypothesis is their population medians identical. And the alternative is not identical, right? So for two independent samples, sometimes they have different sample sizes, like this problem. Usually we define the first sample as the smaller one with the smaller size, and we use M to denote its sample size, and we use N to denote the second sample size, which is usually larger, greater than or equal to the first one. And so usually this first and second is irrelevant with the order of the experiments or data collection or time. It's all about sample size. The first sample is smaller than the second. Then we combine the two samples measurements together as one big sample, and then get the joint rank of each measurement. Then we can calculate the sum of joint ranks of each sample as SM and SM. So for this problem, SM is 76, SN is 152. Because the two samples have different sample sizes, even when they have the same medians, their sample ranks do not, their sum of ranks do not have to be the same, right? So just for curiosity, we can calculate the theoretical maximum and minimum of SM and SN given the sample sizes irrelevant with the specific data. So for SM, if all 10 measurements are in the first to the 10th, then SM should be the smallest, which is the sum of 1 to 10, that is 55, right? And the largest SM should be when the rank, when they all rank the last from 12 to 21, which is that is 165. So SM should between 55 and 165. And our result is 76. Similarly, for Sn, there is also a bug tree. The smallest Sn should be 66. The largest should be 176. So intuitively, for this problem, Sn is relatively small and Sn is relatively big, right? So let's see if this much difference should make us reject the null. So in the textbook, they always use stat exact, and exact p-value is 0.0159. If we use R, the p-value is 0.01587. Pretty similar with the stat exact result. So we'll go through how to use R, and if we do not use R, then we can use a table to indicate us about the conclusion of the null. We'll go to the table later. So for now, given the p-value, let's make conclusions. So such a low p-value, right, indicates that we should reject the null. And there are tables with quantiles available for problems with different sample sizes. Although for this problem, our conclusion is that model A is superior than model B in terms of calculating trigonometric problems, but in reality, it's insufficient for the teacher to recommend model A rather than model B, right? Because this result is just for trigonometric problem calculations. For other problems, maybe the two models are different or similar. So there are all kinds of different functions in calculations. This is just one experiment. So, and also another thing is the censored data. Because the longest time of the two samples is 41 minutes. And this may be because of that the experiment has a time limit, which is 40 minutes, which means maybe one student could not finish all the problems within 40 minutes. So that observation, that measurement is 41, but actually maybe it's longer than 41 if he or she finish all the problems. But WMW can work with censored data because it's not sensitive with censored data, right? Because it's based on Wilcoxon. But t-test does not work well with censored data because t-test is sensitive to censored data, non-symmetry, and long tails, right? Okay, so then here's how we use Wilcoxon to do two-sample Wilcoxon-Mann-Whitney test. We simply define and input two samples like this as numeric vector, and the default test is two-tailed test, so we do not need to define anything here. And then because there are no ties in this data, and the Wilcoxon test in R can return exact p-values when there are no ties, right? So the p-value is also low, which indicates the it favors alternative hypothesis, which means their location, their center, is not equal, are not equal, right? And W here means the M plus N, the total number of observations in two samples. Okay, another way to make the decision about whether to reject the null It's only the decision on the null. It doesn't give us p-value, right? So it's using this Gibbons Ch6 table. Is proposed I think several years later. Sorry, this is not 1941. This should be 1947. Because Wilcoxon sign rank test was proposed in 1947 by Wilcoxon, and this Gibbons Ch6 there are two people proposed this method based on Wilcoxon's method, and this table was made in 1947. So how to use this table? The numbers listed in the table are the largest difference between SM and SM not to reject the null. In other words, this is kind of the upper bound of the confidence interval of the difference between SM and SM. If the difference is larger than this value, we need to reject the null. For example, for our problem, N1 is 10, N2 is 11. So the largest difference should be 36. If SM and SM are within 36 or less difference, then we fail to reject the null. But now ours is one is 76, the other is 155, so the difference is 79, much larger than this 36 here. So we have to reject the null. And also there are other table give quantiles. This is actually 95% confidence interval upper limit, right? And there are also tables give expect a specific quantiles, 25%, 75%. Okay, so computational aspects, we can get exact p-value using Wilcox test in R when there are no ties. Right. All right. And here are more introduction on Wilcox test in R. We can define one sample or two samples. If we define the second sample as null, or we simply skip this sentence here, then that would be a test for single sample. If we define two numeric vectors here, then that's two independent sample tests. If we define paired as false, this means this is two independent sample tests. Otherwise, if we define this as true, it means two sample paired test. And yeah, alternative default is two-sided. If it's one-sided, we just need to define it's either less or greater. And if we compare, if the two samples have the same median, we can define mu as 0. If we want to compare, we want to test if one sample's median is some certain value larger than the second, we can define mu as a specific value as the difference. Then the default p-value is asymptotic. If we want to have exact, then we need to define exact as true here. And for the order correction, the default is true. So if we do not want to have the order rank correction, we need to define it as false. All the true and false should be capital letters, or we can use T or F for short. And then if we want to give a confidence interval of the difference of the median, we can define it as true, give a confidence level. Usually the default confidence level is 0.95. We don't need to define it like this. Okay, more argument about this function here. So the best way to use a certain function in R is to find an example and use your own data to replace those numbers in the example, right? So then let's introduce a test statistic for the Mann-Whitney formulation, the big U. So the big U, which is the function of rank sum S and sample sizes M and N, can be calculated using this equation here. So UM and UN, they have a mathematical relation like this. So once we calculate UM, we can use this equation to get UN. Or if we get both UN and UN, we can use this equation to verify if they are correct numbers. So we only need to directly calculate one of them, UM or UN, right? We don't have to calculate both of them because we can use this equation to get the other one. So to obtain UM or UN, we count the number of observations in one sample exceeding each number of the other sample. Ranks are not needed. We just need to calculate the number of exceedings. So it's the basis for confidence intervals for the median differences. And let's look at an example. So calculate the test statistic U for the previous calculator problem. So because M is 10, N is 11, it's easier to get UN because UN is the sum of the number of observations in group B exceeding each observation in group A. Okay, so yeah, never mind. Calculate both of them are I think the same. So group A has fewer observations, so UN is easier to count. So to count things easily, we can put both samples in ascending order, right? So when we calculate how many does each atom exceed the atoms here, then we can, it's easily to compare and count, right? And then we get UN by hand, right? So how do we get this? This is for UN. For UN, we use group A's each observation 17. 17 is less than all of the observation in group B. So 17 is 11 here. And 18 is also less than all of them. So 11 for 18. 19 is also less than all of the observations in group B. So 19 is also 11 here. So on and so forth. Until here, 33 is less than 5 observations in group B. So the last is 5. So we sum this, get 89. UN is 89. Then we use that equation to calculate UM. Here is MN, M times N minus UN. So UM is 21. Right? It seems a big gap between UM and UN. Then with UM and UN, we can get confidence intervals using tables or programs. The table is the matrix of the difference between any two observations in sample 1 and sample 2. Sorry, between any observation in sample 1 and any observation in sample 2, xi and yj. We use dij to denote it. The procedure treats dij's like wash averages for single samples. Here's the table. Dij matrix, right? Here are each observations in sample 1, horizontal, and the vertical items here are the observations in sample 2. And these are the Dij here. And then the Dij is always use Di minus Dj, right? This one to minus this one. And then a confidence interval is to get a certain proportion of the data in this in the middle. So we may cut off a corner here, cut off a corner here, the largest or the smallest corner, and take the middle range as the confidence interval. Then we need to use programs to get us the number of Dijs we have to exclude. Then with that number, go back to the Dij table to find the number and get the upper and lower limit of the confidence interval. So using R, we can use Q Wilcox. We can get the order of Dij that we start including into the confidence interval. The first value here is the probability of one side corner we need to exclude from the confidence interval. For our problem, because alpha is 0.5, then one side corner is 0.025. The next two numbers are the M and N respectively, and it returns 27. It means the 27th largest Dij and the 27th smallest Dij are the upper limit and lower limit of the confidence interval, right? And then we can use P Wilcox to verify whether 27 is correct. So we can try 26 and 27. And when we try 26, the p-value, so Q Wilcox is given the p-value, given the alpha, returns the order of the Dij we should include. P Wilcox is the opposite, input the order of the Dij and it returns you the p-value. So when the 26th Dij makes the p-value still smaller than 0.025, but for 27th, it's just above 0.025. So 27 should be the first order of difference Dij we include into the confidence interval. So then we calculate 26 largest one on this upright corner, and then get 26 the smallest one to exclude. So all the Dijs inside this shade, inside this range, are with 95% confidence interval. So the upper bound is -2, lower bound is -13. And if it's with a different confidence level, we can use the same way to first get the number of Dijs we need to exclude. For this one is 16. We need to exclude the upper 16 and the lower 16. Then the rest are within the confidence intervals. So it's from -16 to +1 for the 99% confidence interval. We can also use Wilcox test to get the confidence interval. So we just need to set the const.int as true. And because the default confidence level is 0.95, we don't need to define anything here. So it gives us the 95% confidence interval, the same. And it also gives us the estimate of the difference in location. This is the estimate Dij, right? It's -7.5, which means the Model A, Type A calculator on average saves students 7.5 minutes to finish all the problems in that specific set. All right, then the asymptotic approximation. So why do we need asymptotic approximation? Because it's always easy to use z-table, right? To use normal approximation, especially when the distribution is roughly normal, is close to normal, and when the sample size is big enough, and also when there are ties that we cannot get exact p-value using a lot of programs, we prefer to use asymptotic approximation to convert all kinds of test statistic into a z-value, right? So if both sample size is greater than or equal to 15, then we can use normal approximation. 15 is kind of a cutoff line. If a sample size is larger than 15, one sample size is larger than 15, then we can use normal approximation. Not always, but generally it's this. So SM and UM can be converted into Z using these equations because we skip this part, but if you have interest, you can do by yourself. The mean and standard deviation of SM are here. And then the mean and standard deviation of UM are here. So with mean and standard deviation, we can always convert a statistic into z-value, and then use the z-table to get the p-value and confidence intervals. So this is useful especially when we have tie data. We better use a asymptotic approximation, right? So then let's talk about ties. For single sample problems, we use mid-rank rule for ties. And we will do the same thing for two samples. It's just to use the joint rank of those observations in the one big sample, right? So if one observation in sample 1 equals another observation in sample B, that also is a tie, right? So let's look at an example, example 4. Still the same context, the calculator problem, comparing two calculator models. This time the data have ties. And do they indicate difference? So first we got the joint ranking using mid-rank rule. Then we got UN. With UN, we can get UM. So UN and UM again have a big difference. And with UN and UM, we get p-value. It's some evidence against the null hypothesis. Not very strong, but some evidence. So for this problem, we have to reject the null, right? Because this p-value is smaller than 0.05. And for this problem, there are ties, but there are not too many ties. The ties do not seriously upset conclusions. But when there are many ties or the samples are unbalanced, the results would be different. It will affect our conclusion. So for this problem, if we use Wilcox test in R, they will give us the asymptotic results, right? They will always give us a warning message that Wilcoxon do not work well with ties. So the p-value is asymptotic p-values. All right, and again, we can use tables to help us make decision. The Neve table helps us determine whether to reject the null hypothesis. For each alpha value, here there is for each different alpha value, there's a different table. This is for 0.5. for alpha equals 0.1, there would be another table with different numbers, right? You just need to find the right table. The values are the upper limit of the confidence interval of UM or UN. So if UM or UN exceed the corresponding value here, then we need to reject the null. So for our problem, is so what is okay, 11 and 13, right? So 11 and 13 here is 103, and our UN is 135.5. It exceeds 103, so we have to reject the null. That's how we use the table. All right, in R, we can simply use Wilcoxon test to do test with series ties like this one. This is when we do not have exact value of each measurement. We only have the numbers in each range. For group A, there are 3 observations in the range of 10 to 19, and then 6 in the range of 20 to 29, then 2 in the range of 30 to 39, and a group B, so on. So it is like only having the histogram of a data set, right? So we only know the number falling to each range. So for this problem in R, we can use Wilcox test and assign the lower bound of the range to each observation. We can either assign lower bound or upper bound or the mid, the center of each range. It doesn't matter, but what matters is we have to do the same thing for the 2 sample. If we set lower bound for the 2 samples, we both need to assign lower bound, right? The consistency. Yeah. Then we get the asymptotic result for this problem. This one, low p-value, indicates rejecting the null. So in summary, for this kind of data set, we only have the number of observation falling into each range, each bin. For example, if we only have histogram of some data, we can use asymptotic approximation. These are the equations to calculate the mean and the standard deviation and variance of the test statistic T. So what does T mean? So T is the sum of scores of the test statistic based on ranks or tied rank. And Sj is the score of each observation, of observation J. So this score is something we assign like the lower bound of the range or upper bound of the range. So another example, let's once again use the depth ages data for the plants, the data in appendix 1 in our textbook. So compare the median of the depth ages for 2 clans, the Mc gamma and Mc beta. There are some ties in the data. Let's use Wilcoxon-Mann-Whitney approximation. It's a 2-sided test, right? And since sample sizes are 21 and 24 for the 2 samples, then M is 21 and is 24, right? Then we can get the we can use the mid-rank rule to get the ranks, joint ranks for the observations in 2 samples. And we can get p-value. So this p-value is big, so we fail to reject the null. So people's average age for the two plans are the same, are similar. So here's the Wilcoxon test in R, or we can define A and B as data, so it may seem a little bit better than this. All right, that's all for the first section, and we will continue the second section in the second video.